All right, guys, I want to wrap up these notes on parametric equations. We're going to do an application, but I'm actually going to start us off on number 6 here because there's a really important point about parametric equations for us that I don't think I have really spent enough time mentioning. So this is really similar to another example we've tried in the past. I give you a rectangular form of an equation, and I want us to write two parametric equations. Now we can actually, hopefully I deleted this off our notes. We're not going to graph. We're just going to write the parametric equations here. So from the parameter they gave us, we can write one right away. I'll have x equals, for this one, it'll be t minus 1. Now over here, we want an equation for y equals. So from my original rectangular form, I'm going to write my y equals equation. So I'd move the 6 over. I would also throw that negative on the other side. So we're going to have negative x. It would be plus 6 because I subtracted, then multiplied by the negative. And now when I solve for y, I'm really going to have this square root. And normally we'll do that plus or minus, right? So this would be what I'm graphing in a rectangular form, really. But for parametric equations, in our definition, which I'm not sure if I wrote or we looked at the book, but check it out in section 7.5. Both of these parameters must be functions. So we can't get two answers out of them. So technically for this one, you could pick if you want a positive or a negative square root. I'm going to use positive square root because I don't want to make my life more complicated. So for my y equals equation, I'm going to do a positive square root, and then I'll throw x equals in there. So, or sorry, t equals in there for x. So this would be a negative t minus 1 plus 6, which will really simplify to negative t plus 7. So we've got our two parametric equations there. So just want to emphasize that our parametric equations do have to be functions. Sometimes in like this one, we'll kind of get a choice to pick from. All right, so our application we're going to finish up with here is projectile motion. If you guys have taken physics, you may have seen this. We have standard equations for horizontal distance in parametric equations and vertical distance. And projectile motion is when something is thrown or, I don't know, launched, however you want to think about that. So that's going to be an object that follows a natural like projectile path. Okay, so our x distance is going to be our horizontal distance, and that's going to be represented by t is our parameter, and that's time, times the initial velocity, right, which would make sense. Our x distance is going to matter the velocity they throw it, times cosine of theta, which, if you think about cosine or unit circle, is that horizontal distance going through. And theta will be the kind of launch angle, or the angle through which the object is thrown. And I have most of these variables written out up here. So our vertical distance, y, whoops, going crazy there, is going to be pretty much the same thing starting off. The time is our parameter, the initial velocity times sine of theta, right? Which, again, hopefully makes a little sense. Sine is that vertical distance in our unit circle, so it tells how high it is. But then other things come into play. So the vertical distance is going to be affected by gravity. So 1/2 the gravitational constant times t squared plus the starting height of the object. So these are going to be the things right here, like the gravity and the time, that are going to pull your object down, and this original height is where it started. And it kind of makes sense. This is a quadratic equation, so it'll be a negative parabola there going through. All right, the gravitational constant will depend on the problem. We really only have two options, and it'll all be for units. It's 9.8 meters per second squared, or 32 is what we're going to use if it's in feet per second squared. All right, so we'll try out this example here. We've got Kaylee practicing free throws for a basketball game. So I'm going to draw a little situation. She releases the ball with an initial velocity of 24 feet per second. So let me move this over. At an angle of 53 degrees with the horizontal. So I'm going to draw Kaylee over here. Here's her basketball. And the angle she releases it at is 53 degrees. We've got 24 feet per second for velocity. So we're going to use feet for the gravitational constant. The horizontal distance from the free throw line to the front rim of the basket. So let me put the basket up here. Is 13 feet. The vertical distance from the floor, I always do this, gotta delete this guy. Fix my computer here. All right, be better. From the floor to the rim is 10 feet. And the front of the rim is 2 feet from the backboard. So essentially, we want the ball to be in this area for her to make it in, right? Not too much to clear. The last piece of information they give us is that she releases the ball 4.75 feet from the ground. Does she make it in the basket? All right, so there are a number of ways you can approach this problem, but we want to essentially figure out the path of this, and we want to know if her XY coordinate is going to be between these points. So like 13, 10 would be a coordinate between 13, 10 and 15, 10, right? Anywhere up there. So I think I'm going to go about this is I'm going to use 10 feet as my Y, and I'm going to find what X is when Y is 10. And again, there are many more ways to do this. So, but I'm going to go this way. I'm going to find out what is X when Y equals 10. And you can use your calculator for this, but we have equations. And again, there's more ways. So if you want to start with X and figure out what Y is, then you could do that going through. So I'm looking for, well, I'm going to use the Y equals equation. I'll put 10 in there in a second and fill in everything else. So T is our parameter, time. So I'm going to just leave T. The initial velocity is 24. I'm using sine, and the original angle was 53 degrees. 32 feet per second is my gravitational constant here. And 4.75 was my initial height. So starting with that, and again, we can always get the rectangular form. We could pretty much find X value. We have all the things to find X and throw that in here. But I'm going to use my calculator to solve here. And I'm going to just solve by graphing. So I can pull this up out here. I have to go back. I'm in parametric mode right now, which you guys could use, but I want to make sure we're really accurate. So I'm going to throw in my equation. I need to change my calculator 2 degrees. So I'm going to change my mode to degrees and make sure I can see this in the window. My X-min is the horizontal distance. No, X is time here. So I don't need negative seconds. 10 seconds should be playing time for a basketball. And I'm actually going to change that to 5 seconds. I think that's enough. And Y will be my vertical distance. And I don't need any negatives, but I need to see above 10. So I'm going to make that 20. Let's see our graph. There we go. I want to know when it hits 10. So I'm also going to graph 10. And there we go. I'm going to find the intersection. Now this should kind of make sense, right? because the ball is going to go up, hopefully over the 10-foot mark, and then down back into the 10-foot mark. So for us, I think it would make the most sense for her to get the ball in the second time the ball passes through that 10-foot mark. So let's find it on there. So I'm going to second calculate intersection. First curve looks good. Second curve, good. My guess is closer to the second one. I'm going to take it 0.774. Could also solve this using the quadratic equation if you want to, but I don't need that first point of intersection to go through. All right, so now let's check where the ball is horizontally. So I'm going to sub it into this guy. (24) cosine 53. Throw that in the calculator. Make sure you're in degrees. And my answer turns out to be 11.179. Let me just double check that really quick. So I've got 0.774 times 24 times cosine 53. Looking pretty good. So when the ball's at 11.179 feet, it is 10 feet in the air. So that's going to put us here, right? This would be our horizontal distance, 11.179. Our vertical distance would be 10 feet in the air. But the basket's out here at 13, so she will not make it in. What would change so that she would make the basket? Think about that. She could like throw the ball harder. Maybe she could start higher. She could get closer to the basket. She can change her angle, right? All of those things will change our equations. All right, so I want you guys to try out this last one any way you want. Doesn't need to be this way up method up here, but you got to find how far away the golf ball is going to land. If you want to try it and check your answer, it should be 130.148 meters. Careful because you need to use the other gravitational constant there going through. All right, guys, good luck.